Good afternoon, ladies and gentlemen. It's my pleasure to welcome Happ from the Technical University in Vienna as a speaker today. So Leon got his master degree from the University of Heidelberg. His advisor was Ankana Vilan, and now he is a student of Elisa Davoli at the Technical University in Vienna, and he will talk about the extension operators for homogenization that preserves target manifold constant.
Thank you very much for the kind introduction and having me here. So it's a bit funny, I'm doing kind of a travel back in time. I have a feeling with universities. I was in Heidelberg, then in Vienna, and now I'm at like the oldest university of Middle Europe. So that's very nice. It's a great honor to be here, especially to talk in the Nečas seminar, of course. And so, yes, exactly. I will talk about extension operators, which, as the title suggests, like emerged from the backdrop of homogenization theory. To be precise, homogenization on perforated domains. So I don't know if everybody is really familiar with homogenization here. So let me maybe give you a very brief idea what this is about. So imagine you're giving a material some material sample which exhibits small periodically distributed holes of a very fine scale, epsilon, close to 0. So the size of the holes is really tiny. And imagine the relevant physical properties you want to study are given as the solution of some partial differential equation or some system of PDEs or some variational problem. And then often mainly motivated by computational like endeavors, you want to look at some effective limit model where you look at the scale going to 0 of the problem, because it's computationally way more convenient to work on these limit models than to apply some approach for your fine scale problem, basically. And so this is the main idea. The problem is then the relevant functions are always just giving on the like on your material without the holes, obviously. So this is sometimes also called the matrix. And if you look at the limit epsilon going to 0, then your domain will change of these functions, right? So it would be convenient to be able to extend those functions to the holes of your domain. So you only work on a sequence of functions which are really defined on the same domain, for example, for compactness reasons. And I'll come back to this, but just to give you a small idea. And now we will talk about everything in more detail. Oh, we have to point this here. Maybe.
Try to use the keyboard of the computer once it twice. Go back to full screen.
Or maybe I have to go on here. Yes. Okay. So what do I mean by perforated domains? Let's take some periodic set E, which is periodic in all Cartesian directions. So it's translation invariant by adding the different Cartesian unit vectors. Oh, sorry. Oh, this was pointing. Yeah, okay. So we further assume that it's open, connected, and has Lipschitz boundary. And we also take another set omega, which is open, bounded, and again with Lipschitz boundary. So we want some regularity for the boundary there. And for epsilon bigger than 0, we define Q1 as the intersection of the unit cube. So Q will always denote the unit cube here with this predefined perforated set. So imagine on the level of the unit cell, you're now giving the matrix part of your element, and Q0, so the void, is just the complement of this. And then going on, we define the union of the holes for our purpose as the union over all translations of this. As the union over all translations of this holes, basically, but only over this set of integers, such that the holes or the scaled down version of the holes is basically compactly contained in our set omega. So what we do especially is we only take those holes which are well separated from the boundary. And then we define really the matrix part as the complement of this special union of holes. Okay, so in general, if you look at perforated domains, in view of extending functions to the holes, there are two difficulties, two pitfalls in a way. The first one is, okay, the way I set it up, we don't assume that the perforations Q0 are not necessarily compactly contained in our unit cell. And also the complement Q1 must therefore not be connected. So, okay, you now go ahead and think about extending the functions. This can cause a bit of problems, but it can all be lifted in a way so that we will not be concerned with this anymore. This is just to tell you, but more severe is the second difficulty. Because if you would go ahead kind of naively and just define a perforated set as the intersection of this omega with this periodic set E, right? You could also think about this and not taking away the holes at the boundary. Then you could run into problems with extending functions because normally what you have to do is also you have to extend the functions outside of your domain omega. And even though we assume that omega has Lipschitz boundary, and also the holes have Lipschitz boundary, this might not be the case if for like intersections of the boundary of the holes and the boundary of the domain, right? You can easily think of examples where you get a ill-behaving boundary. So that's why we have to exclude them. Nevertheless, you see like our definition sits kind of in the middle of the spectrum of possible perforated domains. You can look at ones where you really only look at holes which are completely contained on the level of the unit set, and then the most general one where you really intersect your omega just with this predefined set E. And actually, the extension operator will be, of course, tailored to the setup I described now, but also for this most general setup where you just intersect omega and E, we will have a corollary adapting to this more general case. Okay, this is kind of what you can think about here. Q0 is not connected. You can also think about, I mean, in this case, it's still compactly contained in Q1, but you can think about like wilder configurations also, just to give you an idea. And as you see here, we just take those holes which are well separated from the boundary again. Okay, the second ingredient is the target manifold constraint I was talking about. So the new feature really with our extension operator that I'm going to present is that we have this target manifold constraint in our problem. So extension operators in general have been around for homogenization, have been around now since 30 years. So especially this one very famous result by Acerbi, Dalmaso, Percivale on Piat from 92, which I will introduce also in a couple of minutes. But they never deal with this target manifold constraint, which is also motivated from applications homogenization. And to adapt to this target manifold constraint, let's assume that we are given some n-dimensional compact connected C2 submanifold of the Euclidean space. You can also think of more general target manifolds. You will have to apply the Nash embedding theorem if your manifold is smooth enough. But what is important for us is really that the resulting submanifold of Euclidean space is C2 compact and connected, right? And then you can define the space of n-value Sobolev maps just by taking those Sobolev maps into RL, which almost everywhere map into your target manifold. Okay, so why do we need to assume that the target manifold is C2? Because we want to work with a well-defined tubular neighborhood and the nearest point projection. For tau bigger than 0, define as n tau, just as the points which have distance less than tau from your target manifold. And this is at the same time already a tubular neighborhood if for each point in this set n tau, there's a unique well-defined nearest point, which realizes the distance to your target manifold here. And then this mapping a point to the nearest point on the target manifold is the nearest point projection. And actually under this assumption that the target manifold is C2, it can be shown that there exists some delta such that this n delta is actually a tubular neighborhood and the nearest point projection is well defined and loses 1 degree of regularity with respect to your target manifold. So it will be C1 on the closure of your tubular neighborhood. Okay, so here the references of the monograph on differential geometry and a nice paper by Foot from 84 with 3 pages, which deals like with these kind of things. Okay. So let's go back to some motivation now that I rigorously introduced everything. The first one is maybe the most famous one, micromagnetics. So it's well known that for ferromagnets below the so-called Curie temperature, named after Pierre Curie, by the way, the magnetization, which describes the magnetic behavior of your material, is subject to a saturation constraint, meaning that it only takes a fixed absolute value. And denoting this absolute value by ms here, we can renormalize our magnetization and rewrite it as ms times this small m, which is a vector field only taking values in S2 then. So there you have a target manifold constraint, n equaling to S2 here. And the second one is, for example, if you look at finite strain elastoplasticity. So you have a plastic strain P, which is usually assumed to take values in the special linear group SL3. And then a common approach is to take it into Sobolev space with some suitable Sobolev exponent. Okay, at this point, I should tell you that our extension operator will be able to deal with the first case, so of micromagnetics, but unfortunately not with the second case. There are two issues here. First of all, SL3 is not compact, and then also it's not simply connected. And we will see that the simply connectedness condition and even a more stronger condition will have to apply to your target manifold to make this extension operator work. But I come back maybe to that issue in the end of the talk. And okay, the first application maybe we have in mind is compactness. So if we look at some toy problem like this, we have on our perforated domain omega epsilon, we are given energy density, which is oscillating with a scale epsilon, and depending on the magnetization and the derivative of the magnetization, where I now take the magnetization field in SL-1. So we generalize this to higher dimensions also. And the density is okay, Theodori, such that everything is well defined, assume P growth conditions. And then there's the question if a quasi-minimizing sequence admits a weakly converging subsequence. Because if you think about homogenization here, you would maybe approach this in terms of the gamma limit. And the gamma limit result always has to be complemented with a compactness result, right? So this is a natural question which arises. And if you apply our operator, it's straightforward actually to show that in the case that P is between 1 and D, and N is additionally P minus 1 connected, so this is the main assumption we'll have to enforce, then you can easily see that you can extract the subsequence. How do you do it? You extend the functions because of the P growth conditions. And if your operator is additionally bounded, you'll get functions on the whole domain of omega, which are uniformly bounded. And then you apply the usual procedure with Banach-Adler-Oghlu, and you can extract a weakly converging subsequence in W1P, for example. Okay, I have to confess at this point that similar results can also be obtained if you use the already existing extension operator and combine it with a nice two-scale argument. But with this one, it's really, with our operator, it's really straightforward to see that you will get a limit function, which maybe I didn't stress this enough, takes values only in your target manifold again. Because of course, if you wanted to use the limit model, you want to preserve the target manifold constraint. Okay, then second application very shortly in high contrast energy functionals. So except of looking at holes, fill them up with a second material. So you get a composite overall, and you add a energy functional on the soft part here with some additional epsilon scaling. So this is why it's called high contrast, because, for example, if you look at elasticity, right? Assume you have some stiff material on the matrix and some soft material on the inclusions, which can be deformed more easily than your stiff matrix. And you think about these as elasticity functionals here or densities. Yes, then you can see that you will have completely different behavior in the holes and on the matrix, and you will deal with some energy function like this, for example. And so you can write this as a contribution from the stiff and from the soft part, stiff and soft from these applications I just told you in elasticity, for example. And then if you have put additional assumptions on the stiff and the soft energy functionals, like standard growth conditions and some regularity, then in some instances, it can be shown that you can really separate the problem of deducing the gamma limit of this energy functionals, which is peculiar for those of you who know, because gamma limits are normally not additive, right? And this will not be really a sum of two gamma limits in the end, but you can basically look at limits of soft and stiff parts separately. And interestingly, the contribution from the stiff part in this case reduces to a usual, I say usual because it's not high contrast than homogenization problem, where you have just oscillating coefficients. So if you already know something of this, is carries over very nicely to the high contrast problem, and you can use it there if you apply extension operators as we do. And below here you can see some papers where this technique of splitting has been applied. So there's a growing body of literature on this. All right, so finally it's time to state the main result. P has to be bigger than 1, smaller than D. Why do we concentrate on the case that P is smaller than D? I may remind you that D is the dimension of the Euclidean space where your sample sits in. So the dimension of the space around omega. Because we will see this later for P bigger than D, basically due to Sobolev embeddings, this problem of the extension operator can be connected to a problem of extending continuous functions to the inside of the holes. And this is a problem well studied in algebraic topology. And there are tools to kind of address it. So this is why we concentrate here on the case that P is smaller than D. And also notice we take about P equals to 1 due to compactness issues, because we need to apply compactness arguments during the proof. And very importantly, we have this P minus 1 connectedness condition, it is called, telling you that the first P minus 1 fundamental groups of your target manifold disappear. To remind you, I mean, P1, the fundamental group, just consists of the homotopy classes of all loops mapping from your unit circle into your target manifold. And the higher fundamental groups are just the higher dimensional analogs of this. You can think of in general like PL as the homotopy classes of functions mapping from the unit cube in dimension L into your target manifold, where the boundary of your unit cube is identified with one single point. So this has to be fulfilled, and then indeed we can prove that there exists an extension operator such that those 3 properties are fulfilled. The first one is kind of tautologic because it just tells you that on the stiff matrix, the function coincides with the original function. But those are the special properties. So you have separate bounds on the LP norm and on the gradient of the LP norm. Why separate? Because in applications it's super useful to have it like this. So yeah, I mentioned it's really separate norms, not just like an estimate on the W1P norm. And very importantly, also this constant here is independent of the scale and also of the domain itself, which will be exploited also later. And this is what I alluded to. We have an adapted result for this most general setting of perforated domains. So if you just intersect omega with this periodic set E, you will get this extension operator, but just for some compactly contained set omega delta. We take the omega delta as the points which have distance at least delta of the boundary. Okay, and it's basically the same result, but again, just for a compact subset. So this is the drawback you have here. And one thing I have to mention is, okay, we have the boundedness of the operator due to the bounds, but the whole problem is not linear. This is due to this target manifold constraint, which is not linear by nature. Because think about S2 again, think about 2 functions on S2. If you add those functions up, they will not map anymore into your target manifold. So why should this be true for the operator? And indeed, you can easily see that this is inherited by the operator. It's not linear anymore. So you lose the continuity, even though we have the boundedness. And we worked hard to get the continuity, but we didn't succeed, unfortunately. So this is open at the moment, if it's true. What we can show is kind of a weak continuity, even though this is mostly not what is referred to if you talk about weak continuity. But what I mean is, imagine on the stiff part, you have a converging sequence in W1P, strongly converging. Then you can choose your extension operators such that the extensions converge weakly in W1P, actually. Why do I say choose? Because as you might see, there is some element of choice in the construction of these extension operators. You have to pick some parameters at some point. And if you turn the screws like mindfully at this step, you indeed can like enforce this weak convergence at this point. Okay, I'll not go into detail or on the proof here, but yeah, at least you have this result on the continuity. What are the tools we use? Okay, so the first very important ingredient is this famous and prominent extension result by these authors I already mentioned from '92 actually, which is used all over the place in homogenization. So if you look up papers, sooner or later you will stumble across this, I guess. So it's the same result as before, but note that here, instead of the target manifold, we just have the Euclidean space. And even if you plug in your target manifold here, you will lose this condition here on the right-hand side. Sorry. Because basically what happens is, for their construction, what they do, they look at the unit cubes. You basically cover the boundary of your hole with an open covering. You take some subordinated partition of unity on each of the covering sets you extend to the inside, multiply with the partition of unity, sum everything up. But then you see that the functions on the outside of the covering, the partition functions will decay to 0. So inside the holes, away from the boundary, your extensions will always be 0. So you will not be able to fulfill any target manifold constraints because, again, your extensions will at some point always be 0. And that's why you lose it. Okay, so we take this result from them. And what do we have to do then? We have to get back to the target manifold. So we will work really in the ambient space of the target manifold. This is why this result is independent of your perforated domain omega in a way, because everything that will happen from here on is in the space of the target manifold. And that's why we will not have to put any additional conditions on your holes in forms of fundamental groups, for example. All these conditions are enforced on the target manifold here. So this is the retraction result. We take some k between 0 and L minus 2. We assume that we have some target manifold, which is given as before. And we put everything in some box. So we assume that for some value R, capital R bigger than 0, actually your tubular neighborhood is already contained in some Q of side length R or 2R. And then if the first k fundamental groups of your target manifold disappear, there exists some closed subset X, which is the set of singularities of your retraction in the end. So there the retraction will not be defined. But luckily it's lower dimensional. So it's contained in the finite union of L minus K minus 2 dimensional planes. What does this mean? If K is 0, this will have at most dimension L minus 2. So this is lower dimensional really. Okay, empty intersection with N. And there's then the retraction on the complement of this singular set in the Q, such that this coincides with the identity on your target manifold. This is what you want to qualify as a retraction. And actually even more on your tubular neighborhood. It's already given by the nearest point projection, which also tells you that the singular set, the set where your retraction is not well defined, also has empty intersection with your with your tubular neighborhood. So the bad points are placed outside of this tubular neighborhood. And very importantly, we have this bound on the gradient. And in particular, this means that the derivative is an LP for p smaller than k plus 2. Of course, this is important because if you want to extend the function, we will want to get a Sobolev function in the end. The retraction should better be also Sobolev, right? I have to say this is not new. The first place where it was applied is this paper by Hart and Lin from '87, where they, okay, as the title suggests, they study maps minimizing the LP norm of the gradient. But among other things, they also construct for Sobolev maps between two manifolds. So you take, as your starting domain manifold, a manifold with boundary, you have a function giving on the boundary mapping into your target manifold, and they construct an extension to the inside of the manifold, also preserving this target manifold constraint. So they are concerned with the surjectivity of the trace operator for functions between manifolds. There they apply this approach already, or they construct this retraction. And this is a connection which is running deeper, actually, so I'll come back to this connection to the surjectivity of the trace operator later. But we kind of adapt this, this approach here. And okay, a nice other work to look this up maybe is this second reference. Okay. Here's a picture. I mean, you see n is just the disk, and delta you can see is this annulus, and then x is contained. So what you see is actually not x maybe, but this is the final union of the lower dimensional planes I'm drawing. Except what is not right at this picture. It's nice to check if you pay attention here. X has dimension most L minus 2. So here x should be a 0-dimensional set. So this should really be a cube in 3 dimensions, such that you can have 1-dimensional singularities. But something like this you can have in mind. How do we construct a retraction? That's the interesting point, I guess. So first you have to triangulate your space. So you take your cube, take away the closure of your tubular neighborhood, triangulate it, and we call tk plus 1 the k plus 1-dimensional skeleton, which is all the faces of your triangulation up to dimension k plus 1. And then we construct the retraction from the inside out. We go from n delta to n with the nearest point projection. Then due to this k connectedness of the target manifold, we can go up to tk plus 1. And from there, we will develop singularities. So we can go up further to the whole space. But this retraction Rs will have singularities, thus the S. Okay, and you have these regularities here. So you can already see that away from the singularities, you're basically fine with Lipschitz. But what about in the singularities? And what will help us there is basically, yes, this estimate here. Okay. Let me maybe shortly tell you something about the construction there. So what you use, let's think in terms of this. So you look at the triangulation. So the triangulation consists of simplices of the higher and higher dimensions, of course. And those simplices are homotopy to a ball. So let's think in just 1 dimension to get an idea. So you will have S1, which is homotopy to your triangle. And we know now that I1 of n is equal to right. So what you want to do is you have triangular space. You assume that on the outside of this face, you have retraction already given, and you want to extend it to the inside of the faces, right? So one here you have given it on the outside of the unit here, and you want to extend it to the ball here. And now what comes into play is this homotopy extension property, telling you that the homotopy extension property is fulfilled if you're given a function on the boundary, which is homotopic to a function that can be extended to the inside, the original function can also be extended to the inside. This is basically assured just by these conditions here. Yeah, because I1 minus n is 0, this means that every function from S1 into n can be contracted to a point. Those can be, of course, constantly extended to the inside. And then the function you started with can also be extended to the inside. So this is why you use this property here. And you can climb up to tk plus 1. And what you do from there on is you are again given the simplex. You will define something like x of the mean value of x. So again, I think here you have the function given on the outside. You want to extend it to the inside, but you don't have this property again. So it is not holding in place here. The straightforward approach is to use exactly this projection to the outside, which develops the singularity here in the origin, right? And so this will be the singular retraction there. But again, I think in this case, if you look at the gradient of this one, this is up to a constant given just by 1 over the absolute value of x, which is nothing but 1 over the distance of x to the singular set of x, which is here just 0. So this is why, this estimate we have is motivated, okay? So why do we choose k equal to p minus 1 in the end? Because all I told you now was just about some k between 0 and l minus 2. This is motivated again by this estimate here. So assume that x is now already given by a l minus k minus 2 dimensional plane. We write, we decompose x as some x prime, which is sitting or living in the plane, and some x double prime in the orthogonal complement. You apply Fabini's theorem, you look at this expression here on the left. You plug in the bound you have here above, rewrite it, and you can see that in the end, the final integral is just an integral of the x perp, and then x double prime to the minus p. And then we observe that the orthogonal complement has dimension at most k plus 2. So for p smaller than k plus 2, which is fulfilled by assumption, this right-hand side will be integrable. So this is why, in the end, we get this retraction as soon as n is k connected. So of course we want to take k as low as possible here, right? To put as least possible assumptions on your target manifold, but you have to choose k as big such that this is fulfilled, such that the singular retraction is integrable actually. So the best choice we can do is taking k exactly as p minus 1, because this is the lowest possible value such that this is fulfilled, and thus the optimal value for us. Okay, one small remark. Before I took k always smaller than l minus 2, you can rewrite this to find out that this retraction result I gave you was only for the case where p is smaller than l. And so what happens if p is still smaller than d but larger equal than l? Okay, you can see that if you assume that the first p minus 1 fundamental groups disappear, in particular this holds in place for the first l minus 1 of them, and then actually this retraction r, which we have here, can already build up to hold on the whole space. So you will not even develop singularities in this case when p is between l and d. So this is the easy case, so to speak. Okay, some further words on this p minus 1 connectedness addition. This pops up also in other places where you talk about extension of functions between manifolds. And interestingly, as you've seen, I mean, with these topological arguments, our result sits right at the intersection between, or at the interface between analysis and algebraic topology. So it's no surprise maybe that also in other places which deal with this interplay, this comes up. So for example, if you look at Sobolev functions between manifolds, as I told you before, you look at the setting where p is between 1 and m, and n is simply connected, then the trace operator is surjective exactly if n is p minus 1 connected. So what we've shown is that for our extension operator, this condition is also sufficient. The necessity is still open. I'll come back to this later. When exactly, as I already alluded to, I will study in more detail like the connection to this problem of the surjectivity of the trace operator. Okay. Then also in the study of the density of smooth functions in the space of Sobolev functions between manifolds, you have a similar result. So C infinity is dense in W1P if and only if n is p connected now. So not p minus 1, but p connected. But if you look into the proofs, the arguments are basically the same. So you can also find the condition there. And then last but not least, also in the Hubel's isomorphism theorem, which is purely theorem, very famous in homology theory, which connects the nth fundamental group with the nth homology group. You have a similar condition, saying that you look at some space X, and if this is n minus 1 connected, then also your first n minus 1 homology groups disappear, and the nth homology groups is isometric to the nth fundamental group. And this is again no surprise, because if you look at the construction of here, of this retraction, where I told you that you use this homotopy extension property, you can also make this more rigorous in algebraic terms, in algebraic topology, and what you use for the proof is then exactly the Hubel's isomorphism theorem. So you can find it there again. Let's go to the proof now of the extension operator. We will do everything for scale actually equals to 1, because otherwise you can just rescale your domain. And you will find that this is important here, that the the constant C for the LP bounds that you derive, the constant is independent of the scale epsilon and of the domain. So rescaling the domain doesn't change anything about the constant, so we can do this. And then for arbitrary epsilon, we define our operator as some rescaled version of the operator before. Okay, simplification. So we now really assume that the voids are completely contained in the unit cube, because this makes computations now a lot easier. This is to circumvent kind of the difficulty one I told you at the beginning. You can deal with it, but the proof gets a bit more complicated, so I will avoid this here. And because we take out the holes intersecting the boundary, we can always assume that we can extend functions to the outside because the boundary is Lipschitz. So let's assume that our set is given as something like this, just some union of squares. So we can just work on one reference cell and get the rest by translation afterward, basically. What you really have to make sure is that the constant that you get for the estimates is independent of your scale. Okay, we take some f, which is now in A1. So A1 is the analog of the stiff part of our omega, but just on the scale 1. And I just renamed it for convenience here. So we extend to some f tilde with this already known extension operator. We use the target manifold constraint, right? Note again, we have the 1 instead of the epsilon here. Then we want to apply our rejection operator. Unfortunately, what we have to make sure is that the Sobolev function f tilde here doesn't take values too much in a measure theoretic sense in the set of singular points of our retraction, because otherwise, if we compose this function with the retraction, this will not be well defined. What we want to use is Sart's theorem, but this does only apply for sufficiently smooth functions. So what we use, we approximate this f tilde by smooth functions fk and c infinity, okay, which strongly converge to W1P. And then we can apply Sart's theorem. The way we do it is the following. So Sart's theorem tells you if you have a sufficiently smooth function, a set of critical values has a vanishing in the back measure in your target space, and we cannot assure that really these f tilde take values in your set of singular points of your projection in a set of measure 0. So it can happen that they actually map into the or also the approximations map into the set X for the P. But with Sart's theorem, we can show if we just alter the projection a bit. So we translate it by some small value h. So we define this ph as py minus h here. Then by Sart's theorem, actually the pre-images under those sets of singularity x plus h, the pre-images under this f tilde k for almost every h has a measure 0. So for almost every small h, actually this concatenation of these two functions is well defined. Then you have the problem, okay, we apply these translations of the projection. So imagine you have points which are in the target manifold, we translate the projection and project back. You will not land in the same point anymore. But since you want to have the extension property that, of course, on your matrix part, your extended function should coincide with the original functions, you have to apply the inverse of the projection again, but only of the projection restricted to the target manifold. And because we take h actually small, this restriction is nothing but the nearest point projection, and you can invert it, and then you look at this, this concatenation for every k. Okay, and then by Sobolev embeddings for suitable p, we find a limit function, and this is actually our candidate. So we define our extension operator as this limit function, and we have some pointwise representation to go with it for suitable x, which doesn't hold everywhere, I have to say. So the limit function does not look everywhere like, again, one of these concatenations here. But okay, so how long do I have until?
I'm still about the water.
Okay, perfect. Let's look at the LP estimates for the derivative of the extension operator. Those are relatively straightforward, I would say, because actually looking at the step where we apply Sart's theorem again, what you can find is that integrate again over B sigma. And B sigma is now, so sigma is very small. And B sigma is the value of all possible translations of this projection operator. And we know by Sart's theorem for almost every H and B sigma, this translation and the composition actually of this Fk and the projection is well defined. So these integrals are well defined. We integrate over B sigma, and you can massage like the equation a bit. And what you find is that this is bounded by some constant, and then actually the LP norm of the derivative of your Fk tilde here. And so if you apply a variant of the mean value theorem, then you find that this quantity here is bounded by, okay, the right-hand side over the measure of the ball B sigma here times this quantity. And since we fix sigma, this is really a fixed constant for us. And to get actually from here to here, you just use that this is really the nearest point projection, which is Lipschitz on the closure of L delta actually. So also the inverse will be Lipschitz. So you can just pull out the constant here and get this line of estimates there. And this overall actually will, in the limit, if you pass the limit in K, this will give us the LP estimate for the derivative. So that's very nice. However, the LP estimates just for the extension were surprisingly, let's say difficult to get, especially for the case that 0 is not an element of your target manifold. Because, if 0 is an element of your target manifold, because if it's not, I will show you the slide in a second, then you know that your target manifold is bounded from below and above. And then by a simple trick, you always get the LP estimate. But if 0 is in your target manifold, actually you have to apply some contradiction argument to show that on the level of the unit cube, you really have the estimate you want. So the LP norm of your extension is bounded by the LP norm of the original function. Then you know actually that this is also true on all of the translated cubes. And then if you put this together, you just write the integral over A as the sum over all translated cubes, because as I said, on the simplification slide, we assume that our set A is just given as some union of some squares. So we can write this just as the sum over these different squares. There we apply the estimates we have, and we get out in the end with the total LP one that we wanted. Okay. What in the case that 0 is not in N? As I said, the target manifold is bounded from above and below in the sense that every Y in N can be estimated from below by some gamma 1 and above by some gamma 2. And then if you look at the LP norm here, you can just pull out the supremum here of this value, because it's always an element of the target manifold. You get gamma 2 to the P. And then you introduce here the integral of omega epsilon, again, over the extension, which is an element of the target manifold. So this is always bigger than gamma 1. So to compensate for this new term, we divide by gamma 1 P times the Lebesgue measure of omega epsilon. And then you use that, actually this fraction here looks in the limit like 1 plus the fraction of Q0 over Q1. So this is also constant. This remainder will vanish in the limit. So you can bound this as you can see here, times actually the LP norm of F, the original function again. So this is how you also get the LP estimates. Now finally to the connection to this trace operator, I now alluded to several times already. This is the relevant literature if you want to look something up on the topic. So again, this Hart and Lin paper was the starting point, I would say, of the research on this, where also this retraction is first introduced. And then very importantly, so when they use the retraction operator to construct these extensions of a Sobolev function between two manifolds, they actually also show that this P-1 connectedness is sufficient for this extension to exist. In this paper, they show that it's also necessary if N is simply connected. So, and this necessity is actually what we are missing. And so that's why this is interesting for us. And okay, here in this case, the arguments are augmented in the sense that they also look at target manifolds which are not simply connected. Actually, this is also already done here, but they complete the results obtained in this third paper. But before I go into detail on that, let me introduce some notation to establish this connection between the two problems. So we assume that del M here is some d-1 dimensional hypersurface of RD against the two regular connected compact and boundaryless. So for example, think of del M as the boundary of your holes on the level of your unit cell. So we change perspective here a bit. We're not looking again at the whole perforated domain. We take out one cell, and in a way, we assume that the cell is that the hole is compactly contained in your reference cell. But nevertheless, this is enough to study the necessity, right? Because if we can say that already on the level of unit cell, there's no chance to extend the functions to the inside of the holes, why should this hold on the whole perforated domain? And then we have these two related questions, or I will show that they are related. So under which assumptions on M and N does the following hold? M epsilon, you have to imagine as M as some annulus around your manifold M. So you have this hypersurface, on the inside lies your your domain manifold M, and then M epsilon is some annulus on the outside, and we want to extend functions from the outside to the inside. And if this Px is fulfilled, this just means that, or this EP space is the space of all functions which can be extended from the annulus to the inside. So if the two spaces coincide, this means that actually every function can be extended to the inside. On the other hand, this property P trace or PTR just means that every function from the really only the boundary, not the annulus, but the boundary can be extended to the inside. So this left space here is the trace space, and the right is just the fractional Sobolev space. And if you take away this target manifold constraint, you know that those spaces coincide, right? But that's not necessarily the case for if you take a target manifold constraint. And also interestingly, if you take away the target manifold constraint, you see that it's easy to see that both problems are equivalent to one another, because you can differentiate between the task of extending functions to the inside or the outside of your problem. So the one direction is in any case obvious, because take a function on the annulus, you can always take the trace on the boundary, and if you can extend trace functions to the inside, then you can extend already the whole function to the inside. And what about the other direction? So again, if you relax this condition, you don't look at target manifolds anymore. There's a well-known you extend basically, and if you know that you can extend functions from the annulus to the inside, you can also extend every trace function first to the outside, to the annulus, and then to the inside again. And so, should I do something? Is it the way?
Oh, the left.
The leftmost, yeah. No, I have to. Oh, yes. Okay. So what about the necessity then? Now to the case P is bigger than D. I told you in the beginning that we exclude this case from our analysis because of the following argument, basically. You can show that the both properties are always equivalent in this instance, because of Sobolev embeddings, actually for P bigger than D, your functions are always continuous already. And so if you take functions on the boundary, so again, this direction is always obvious, right? Going from the trace property to this extension property. On the other direction, what we want to do, we want to extend functions from the boundary to the annulus, preserving this target manifold constraint. If you work with continuous functions, you extend them from the outside because they are continuous. They will not go away too far and away from your target manifold. They will always range in this tubular neighborhood, and then you can project back. So you will always get functions on the annulus only ranging in the target manifold. Okay, for the limit case, you can basically show the same. So they're actually equivalent for P equals bigger than E. But then it's also known that, this trace property is kind of for the same reasons equivalent to the same question, but for continuous functions. So can every continuous functions from the boundary can be extended to the inside? And so this is a very common problem in algebraic topology. It depends on the, with like similar reasons as I showed you here. This depends on the topology of M and on the topology of N again. But there are tools to approach this. So yeah, there are already instruments to tackle this problem, and this is why we concentrated on the more interesting case in way that P smaller than E. Okay, and so what if now P is smaller than E? In general, if you extend the functions to this annulus, they will not range anymore in N. But what you can again do is apply this retraction operator I introduced before, right? So if N is additionally P minus 1 connected, then you can again establish the equivalence of both problems. You extend functions to the annulus, retract them back onto your target manifold. So very interestingly, as for the completely unconstrained case without a target manifold, both problems are again equivalent, and they are actually both solvable simultaneously. For the reason that if your target manifold is P minus 1 connected, this problem becomes again independent of the topology of the target of the manifold M. So decouples from the topology of M, everything happens again in the ambient space of your target manifold. So you cannot distinguish once again extending to the outside or the inside. Neither of those poses a problem for you. So both problems are equivalent again. Can you show more? Okay. What if N is not simply connected? Then there are only partial results available. So this is a very open question, and also for the question of the surjectivity of this trace operator, this is quite open at the moment, because in this, let me go back, in this fourth paper, it's only shown that for a special range of P, and if your target manifold is not simply connected, but still your first fundamental group is finite, then you can extend every function to the inside of your manifold M just by looking at a lifting from your target manifold to the covering space. Because your first fundamental group is finite, you can see that the covering space will be compact and actually also simply connected. So if your target manifold is simply connected, is not simply connected, but still the except the first fundamental group, every other fundamental group until P minus 1 is disappearing, then for the covering space will actually be again P minus 1 connected. So you look at you lift the functions, then you can extend the functions on the level of the lifting, and then you can kind of project back to your target manifold. So this is why under the condition that yes, P is between 3 and E, and if this is finite, they all vanish, but also now M is simply connected. So you kind of shift the simply connectedness from M to M. So not everything is happening again in this target space, but you need the simply connectedness of M now. Then they are also equivalent. So, and also again, simultaneously fulfilled. So also in this case, we can hope to have a necessary condition. And this is why at the moment we can hope maybe for extend our extension operator result also to the case where the target manifold is not simply connected. For example, in plasticity, right, which I told you at the beginning, when you assume that the P only ranges in SL3. Okay, SL3 again is not compact, but let's look at SO3 maybe. Problems where you range in SO3, this will be compact, not simply connected, but the higher fundamental groups will disappear. So you can we can hope to extend, our operator maybe also to this case. Okay, so let me just quickly sum up what I told you. So we have seen the construction of some extension operator on perforated domains, which is in a way scale dependent, because these separate LP estimates here come with a constant which is really independent of the scale. And the important condition was that your target manifold is p-1 connected. Of course, the general question is, can we construct this extension also if this p-1 connectedness is not fulfilled? For example, if the first fundamental group is not zero, right? The question is if C is really necessary as for the surjectivity of the trace operator. We don't know that at the moment. And also, what about the connection to this trace operator actually? What about the necessity of the surjectivity of the trace operator for this existence of an extension operator for more general n? We also don't know anything about that. Which, yeah, also has to do with the fact that the surjectivity of the trace operator is not fully explored at the moment. So there's also a lot of work to do at this point. And yeah, with this, I'm at the end. I conclude, and I thank you very much for your attention.